Hi everyone, I'm very happy to be at ITCS 2022 to talk about my recent work, more dominantly truthful multitask peer prediction with a finite number of tasks. So let's start. Considering we have two people here and they are asked to rate several restaurants, and we want them to provide their honest, high quality reviews. So what we're gonna do is we're gonna take their feedbacks, whether they like it or dislike it, as our inputs, and then we're gonna use a reward system to calculate their reward and to return the reward to agents here. Okay, so for these reward systems, one way we can one traditional way to design it is we just use flat payment. But the problem is that actually gives the two agents no incentive to rate these restaurants. And another thing we can do is we can do this spot check, randomly pick a question, a rating task, and to check whether they tell the truth or not. But it is impossible because they are actually providing their subjective opinions and there is no way to check it. And the third thing is, okay, maybe we just pay these two agents based on the number of agreements they have. Like for example, if there are five restaurants, they have the same opinions, we're gonna pay them $0.5 or something like that. But the problem is, first, it's possible that Alice and Bob, they have very different tastes. And in such case, even if they tell the truth, they may have very little agreements. And in such case, they will not be incentivized to tell the truth. And another is if we tell them we're gonna pay you according to the number of agreements, what they can do is they can just ignore the identity of the restaurant and they just say they like the restaurant all the time. In such case, they don't need to pay any attention, they don't need any effort, but they can get the highest amount of payments. So that will distort their incentive. So that is actually comes to the question here is we want to design proper reward system that can avoid these issues, can incentivize them to provide informative reviews. And this question is called multitask peer prediction, and it is first proposed by Dasgupta and Ghosh in 2013. Okay. So to address this question, there are other work, but today I'm going to introduce a kind of framework. One framework is called the mutual information paradigm. And in this framework, so the trick here is that first we're going to see, for example, we have infinite. So let's just say we have infinite number of restaurants or rating tasks. And we can see Alice and Bob, their feedback as IID samples and of some maybe random variable x and y. And then because we have infinite number of these IID samples, so we can estimate the joint distribution between x and y, and then we will use this definition is mutual information defined by Shannon. And the mutual information actually calculates the correlation between x and y, and it takes the joint distribution of x and y as input and outputs a non-negative value. So let me explain what is joint distribution here. So let's see, if they like it, we say yes. If they don't like it, we say no. And this is the joint distribution here. It's we can also think it as 2x2 matrix. So this is actually the probability that for a random restaurant, both Alice and Bob like it. And this is the probability for a random restaurant, Alice likes it, but Bob doesn't like it. So this is this joint distribution, like joint distribution matrix. Okay, so the point is that the mutual information actually measures the correlation between X and Y. So in such case, if Alice and Bob, they have very similar tastes, they're gonna have very high correlation. But even though they have very different tastes, they can still have very high correlation. It's like maybe it's negative correlated, but doesn't matter. Mutual information is non-negative. So this kind of the way to kind of like pay them the correlation to incentivize them to provide informative. And the behind the mathematical reason is here. So let's first see this running example here. So the point is that, for example, this 0.4, 0.1, 0.2, 0.3 thing is the original joint distribution between Alex and Bob's reports. And maybe Alice, she can actually perform a strategy. And the strategy, we can just see, this strategy just means that if Alice likes the restaurant, she's gonna say she likes the restaurant. She's gonna tell the truth. And this column means here, if she doesn't like the restaurant, with 0.5 probability, she's gonna say she still likes the restaurant. So this strategy actually is like less informative strategy. And the point is that if we use mutual information, as long as Alice perform a strategy, the mutual information is going to be smaller. And this is a mathematical form, is that previously the joint distribution is U, and as long as Alice performs the strategy, is equivalent to as we multiplying a transition matrix. And here this transition matrix is like every column sums to 1, and they are like elements are non-negative. And it's the same as we multiply a transition matrix on the left, and this is called the data processing inequality of mutual information. It guarantees that this will decrease mutual information. So so the point is that because mutual information satisfies data processing inequality, thus if we pay them according to this, their strategy will decrease. Their strategy is also a data process method, and their strategy will decrease their payments. So that is why, in this paper, we just call it dominantly truthful. And it's just like the strategy decreases their payment. So like for Alice, regardless, Bob gonna see she shouldn't perform any strategy here, and it's same for Bob. So that is why if we use this mutual information paradigm, we can naturally have this good incentive property. Okay. But the problem is, like one thing I kind of mentioned before, it actually needs infinite number of tasks. Like the restaurants, they need to rate an infinite number of restaurants to perfectly estimate the joint distribution. And what if we have only 10 tasks, like 10 restaurants? And in such case, we can only get a frequency matrix. It's like we just get empirical frequency. And if there is only 10, it's not even a good estimation. And one solution is like, we can usually assume that Alice and Bob, they only care about their expected payments. And in such case, an unbiased estimator of mutual information is sufficient. But however, the Shannon mutual information doesn't have an unbiased estimator. It's because I'm not sure whether you remember or not. So in the definition of the Shannon mutual information, which I won't write in detail here, but it has a log function there, and this log function you just cannot estimate it with finite, unbiased estimated with finite number of tasks. So in such case, we need a new definition of mutual information. But still, we want to satisfy data processing inequality. And also, the most important thing is we can unbiasedly estimate it with finite number tasks. And that is this work proposed the determinant-based mutual information. So it's actually a very natural definition. So remember the joint distribution matrix we mentioned before. The reason I write it in a format of matrix just because of this. We can naturally define the mutual information between two random variables as the determinant of their joint distribution matrix. And we just take the absolute value to guarantee it's non-negative. Okay, so this is the running example here. Okay, so the determinant-based mutual information naturally satisfies, this should be capital U here, naturally satisfies the data processing inequality because the determinant actually satisfies the multiplicative property and the determinant of the transition matrix is always less than 1. And also, the important things here is remember that we may only get empirical frequency matrix. It's like they rate 10 restaurants and 3 of them, they both like it. 2 of them, one like, one dislike, and 1 of them, they just don't like it. We get this empirical frequency, and by some transformations, we can actually prove that in expectation, the determinant of this frequency matrix is actually proportional to the determinant of the joint distribution. And you may ask, then, this absolute value, how can we deal with that? And the trick is we just use the square. And if we use the square, we can actually divide the tasks into 2 parts, using one part to estimate something and use another part and then multiply them together. You are referred to the paper for more details, but the point is, the thing I just want you to know here in today's talk is that the reason this thing is true is just because the determinant actually has a polynomial format, if you remember the formula of the determinant. And it's also if we square it, it's still a polynomial. And this is the fundamental reason it can be unbiasedly estimated by finite number of tasks. For example, if we talk about this binary case, and this is they both like it. This is the joint distribution matrix. And this is maybe they both hate it. Okay, for example, if we want to unbiasedly estimate this very simple. We just need one task, right? We just need one task. And we set up our indicator random variable, whether they both like it. If they both like it, it's 1. If they otherwise, it's 0. In such case, expectation is this thing we want to. And if we want to unbiasedly estimate the product of these 2 values multiplied together, we just need 2 tasks. And actually, remember we assume the IED, every task there is independent IED assumption there, and we can just set up 2 indicator variable. This is for the first task, and we multiply the second task. And the point is that in such case, because the tasks are independent, so in expectation, it equals the expected. This is for the first task. This is for the second. And in expectation, we can just decompose it, and the expectation of this is this, and the expectation of that is this. So that is why. So the point is that as long as we just want to estimate the polynomial format of the elements in the joint distribution, we just need a finite number of tasks. And in fact, it depends on the degree of the polynomial. If the polynomial's degree is d, we just need d tasks to unbiasedly estimate it. Just use this. Okay, so that is a fundamental thing here. And remember, in today's work, we will talk about more dominantly truthful mechanism. And the previous process actually reduced this mechanism design question to information measure design. And remember, as long as my information measure satisfies two properties, then we are done. The first property is data processing inequality, this one. And this one guarantees that dominantly truthful strategy decreases payment. And the second property is very important, is it should like the determinant-based mutual information. It should have a polynomial format. Like, remember the previous process I performed in the previous slide. As long as it has a polynomial format, it can be unbiased estimated with a finite number of tasks, and the number of tasks we need is the degree of the polynomial. So, okay, so to address this question, we are essentially trying to find the information measure that satisfies these two properties simultaneously. That's the key. And here comes to the most important slide in this talk. And if you understand this slide, it's like just, I think this is all thing you need to know for this work. Is this new definition of mutual information called volume mutual information. Okay, so the volume mutual information. So first we see here. So the data processing inequality there is like, remember, we want to find mutual information for all transition matrix, for all joint distribution. We want to have this inequality here. And this transition matrix multiplied on the left actually defines a partial order. So the reason why this is partial order, because if you multiply some transition matrix on the left and you multiply it again, the product of the two transition matrix is still transition matrix. So that naturally defines a partial order this way. A joint distribution is less than another joint distribution as long as we can find a transition matrix such that U prime equals T multiplies U, and this is the partial order. And the data processing inequality essentially means that we want to design a monotone function on this partial order. So one way to define a monotone function on partial order, one very natural idea to define monotone function on partial order, is that maybe we just try to count how many, for one joint distribution, we just try to count how many joint distributions are less than it. And maybe this is improper it, but I don't know whether it helps you to understand it. But if clever is something satisfy partial order, and if you want to know how clever you are, you can actually count the number of people that are less clever than you. And the point is, if it satisfies partial order, then someone is less clever than you. Like the people are less clever. If someone is less clever than you, and then people less clever than him or her is also less than clever than you. So this is maybe inappropriate. So the point is that is this partial order thing. It's like, it's natural. It's, we can just define how informative a joint distribution is by the number of joint distributions that are less informative than it, and we use this as a definition as less informative. And we actually call this the lower set. For every joint distribution, we call the joint distribution, we call the set of all joint distributions less than it as its lower set. And the volume mutual information is defined, it's actually a continuous set, it's not discrete. So we define it as the volume of the lower set. And still, I want to say that the fundamental reason is that because it satisfies partial order, so if U prime is less than U, then we have this set theory thing. It's like the lower set of this U prime gonna be a subset of the lower set of U because it is a partial order. And in such case, the volume gonna be smaller than the volume U, and then this actually naturally defines a monotone function on this partial order. So this is the idea behind the volume mutual information. Okay, and this is why it naturally satisfies data processing inequality. Okay, so that's how we define the volume mutual information. We get the joint distribution matrix and we calculate the volume of its lower set defined on this partial order. And remember that we can actually use, when we calculate like this is like something in this space, and this may be U, and this may be U prime. And in this whole space, if we calculate the volume, we can actually use any density function we want, as long as this density function is non-negative. And so forget about this. This is not important. This is not important. And the point is that we can tune the density function, but still satisfy this monotonicity, which is another term for data processing inequality. And if we use uniform density means like the density is equals to 1 everywhere. In such case, interestingly, we can prove that this volume mutual information is actually the determinant-based mutual information. And another very interesting property is here. If we use polynomial density, like the density is a non-negative function on the space of the joint distribution. If we use polynomial density, we will get polynomial volume. It's not directly, you still need to multiply something, but the point is we can get polynomial volume mutual information. So actually that solves our question, right? Because the definition of the volume mutual information naturally satisfies data processing inequality, and also we can prove that if we can set our density function as any polynomial, as any non-negative polynomial as we like, and we can get a family of polynomial volume mutual information, and that gives us a family of new dominantly truthful mechanism, and we only need a finite number of tasks. So that actually solves the question. Okay. And actually, to want to give more intuition here, so let's consider the binary case. So everything we talked about before, although previously I used binary case as running example, but everything I talked before actually applies to non-binary case. Okay, so this binary case, considering we have this 2x2 joint distribution matrix, and this should sum to 1, and everyone is non-negative, and we can use XYZ because W has no freedom here. We can use XYZ as the space, but to have a better visualization, I actually use STP here, and we can prove that all possible STP equals all possible this joint distribution matrix. And so the reason I use STP here, because both ST and P, they belongs to 0 to 1, And if we use x, y, and z, and they have some constraint there, so I use STP here, and then the distribution, all possible joint distribution can be seen as a cube. And then we just pick, so this is because I want to correspond here. So then we pick a slice of this cube, and it's just we fix P. We fix P, and in such case, we only have S and T as our variables. And in such case, we can actually draw, so if U is the joint distribution, and we want to draw the lower set. Remember, the lower set is all possible TU, and T is all possible transition matrix, and this is the lower set of U. And in such case, this is a convex set, and we just like draw the corner here, which corresponds to 4 transition matrix, identity transition matrix, permutation transition matrix, all 1, all 0, or something like that. And in such case, this is a convex set. This convex set is actually this blue, sorry, it's not blue, it's green area. And we can see that if we draw some, for example, if we draw some U prime less than U, and within this, and we can see that the lower set of U prime is going to be something like this. And it belongs to the lower set of U. Okay, so that this can give you some intuition, some visualization in your mind for this lower set distribution spacing. And the thing is that we can tune the density and get very different volume mutual information. So here I just show everything in one slice because it's easy for us to visualize it. And so this volume mutual information here, this is a contour. This is the contours here. Okay, so remember that we're gonna use this, we can tune every density we like, and I'm going to show you 3 different density functions. And this is the plain one, is the uniform density. And in such case, so this is actually the volume corresponded is actually the determinant based mutual information, because I said before the uniform density leads to determinant based mutual information. And this is the contour. And if we can also use this mountain or basin shape, and it gives you very different contour shape. And the point of this figure is just shows that it's possible that we can just like tune the shape of the density function to tune the volume mutual information. And if in some scenarios you figure out you want the contours to be like this, then you can use this density. If in other scenarios you want the contours like this, you can use that density. It's very flexible. Okay. And another thing I want to mention here is like one mutual information, a very artificial mutual information is this. So we just like define this set a threshold, and for the joint distribution that is more informative than this threshold, we give them 1. Otherwise, it's 0. So we call this like threshold mutual information, and it actually corresponds to a threshold payment scheme. But the same thing. We just need infinite number of samples rating tasks to estimate the joint distribution. And so if we only want a finite number of tasks, we just want very natural idea. We just want some polynomial to approximate it. And we cannot directly use polynomial to approximate, because it may violate the monotonicity and also violate the dominantly truthfulness. So the thing we can do here is, so this threshold mutual information, actually corresponds to the volume mutual information, why we actually set this threshold with infinite number of density and zero otherwhere, is direct delta function. And in that case, remember this volume mutual information. So if we use this density, the direct delta density, we can get this threshold mutual information. And in such case, what we can do is we can use polynomials to approximate the direct delta density, and then it's corresponded to a volume mutual information which is polynomial. It's also polynomial, and it satisfies data processing inequality, and more importantly, it actually approximates. So we can see like from this way we get like better and better polynomial approximation for this direct delta density, and we're gonna get better volume mutual information to approximate it. Okay. And the reason I mentioned the threshold thing, because in the paper I didn't cover in this talk, is that this paper actually provides a tractable effort incentive optimization goal, but it has some like model constraint there. It's discussed in the paper, but the point is that with this effort incentive, like in some situation, we can prove that the threshold mutual information corresponding to the threshold payment scheme actually can incentivize the effort the best. And in such case, if we want to use that mechanism, but still with finite number of tasks, we can just use the trick I mentioned before, use the sequence of volume mutual information that can actually approximate the threshold payment scheme. And also it is, I mentioned before, polynomial, satisfy data processing inequality, so everything is fine there. Okay, so this actually concludes this talk. This work actually provides a family reward system and the volume mutual information mechanism. And it's like we first get the volume mutual information, and then we just use a finite number of finite samples to estimate it, and then we can use this estimation of our payment, and that is the definition for the volume mutual information mechanism. And because the volume mutual information satisfies data processing equality, we can prove that it has strict dominant strategy, truth-telling equivalent informative strategy, and also it doesn't need any prior knowledge and only requires finite number of tasks. And I think for the future work, in addition to like empirical validation of this mechanism, one thing I think can be interesting is to apply this volume mutual information in other areas, like design the loss function in the learning scenario. So one constraint I want to talk about here is like, although this volume mutual information actually satisfy the property, determinant-based mutual information also satisfy, but it can have very complicated formula, and maybe the human agents, it's not easy for them to understand the reward system if they want to understand it. But if we can apply it in the learning scenario to incentivize, to design loss functions, we do not need to have that issue. And also it's very flexible. It's like we can just like tune the density and to get any shape contours we like, and that may have like that can be nice in some scenarios, I hope. So this is one future direction I think may be interesting to explore. And thanks.